Okay, we've talked about how to compute the torque due to a force acting at a single point, which is, say, is just the moment arm times the force, or various other versions for the torque. But a real object is made of lots of atoms, and gravity acts on each one. It would seem like computing gravitational torque would be tedious at best and impossible at worst. But in fact, it's pretty simple. Every object has a special point called its center of gravity, sometimes symbolized by CG. For the purpose of gravitational torque, we can act as if the entire weight of the object is acting at the CG. Over here we have the diagrammatic symbol for CG. The motion of the CG tells us about the forces and torques. You often see this symbol on things like crash test dummies or other things where you're going to track the motion. People put this symbol in that way. We can also tell how it spins by just measuring how that thing spins. The center of gravity is functionally the same as the center of mass that we talked about earlier. The reason for the difference is if your object is large enough, or your scale is large enough that you have to worry about varying gravitational fields, then they won't be exactly the same place. The center of gravity is defined as the place where gravity acts. The center of mass is the mass weighted position that we talked about before. So generally, on the Earth, where gravitational strength is uniform and constant, they are the same point, and we really use the two terms interchangeably. But in a more precise application, you have to be a little careful. If the gravitational field can vary, then the center of gravity will be different than the center of mass. Note that something suspended at, or directly above, or directly below its center of gravity will have no net torque on it, since the weight's line of action will pass through the pivot and have a moment arm of 0. Such an object would not spin under gravity. So we're talking about if we had some shape like this, and we suspended it here with its center of gravity here, that would be a line of action that looks like this, and therefore the moment arm is 0, so there's no torque about that pivot point. That leads to something called the balance principle. An object, or a collection of objects, is in balance when its center of mass is directly above or directly below the point of support. In such case, the force of gravity passes through the pivot point and has a moment r of 0, so gravity will exert no torque. The object will remain balanced. Obviously, you can put it out of balance by pushing on it or whatever, but left to its own devices, it's balanced. So here, in this one, we can see that the center of mass of the bottle and wood collection, well, it's supported here, so it has to be in this line. Oops. Somewhere in this line. The center of gravity of that system has to be there. Now, we've cheated a little bit down here. Notice we have the wider little bit here, so there's like a little bit of leeway that lets you adjust this. Because otherwise, while in principle we could balance it on a point, it would not really stay balanced there because it would be hard to actually get it exactly stationary, and small air currents and stuff would just tilt it over. By having even a relatively small support here, we can tell that the center of mass is above at least this region. Notice that does mean that this whole swath here, that is the center of mass now. Somewhere in here is the center of mass of the system. The Coke is a little bit more massive than the wood thing, so I would guess that the center of mass is probably something like over here. But it's not clear to me. We haven't measured or anything. All right, let's do a problem. A 1 meter long dumbbell has a 10 kilogram mass on the left end and a 5 kilogram mass on the right. Find the position of the center of gravity, which is the point where the dumbbell would be lifted in order to remain balanced. Remember, this is the same as finding the center of mass. So this is mostly, do you remember how to find center of mass, to remind you from the Unit 5 stuff we did. The center of mass is defined as the total mass times the center of mass position is each individual mass times its own position, summed up. That's the one I like. You can remember it with the MT divided over the side. We'll end up doing that in a second anyway. So here, our total mass is 15 kilograms times the thing we're looking for. And then we have, I'm going to put, we said measured from the 10 kilogram mass. So 10 and 5, which means that the problem sets our origin here. So we have 10 kilograms times 0 meters plus 5 kilograms times 1 meter, which of course is just 5 kilogram meters. And when we do that division, we end up with that the center of mass position would be 5/15ths of a meter, or of course 1/3 meter. So the center of mass of this system would be something like over here. If you wanted to lift this in a balanced way, you'd have to lift it there. And we can see what's going on here is that the torque due to the 10 mass is now balanced by the torque due to the 5 mass. And so we're starting to see back that this is really just a statement of balancing torques so that the gravitational force doesn't exert its own torque about our lifting point. All right, which point could be the center of gravity of this L-shaped piece? Assume the bar is uniform. One of our things to look at here is that the center of gravity doesn't actually have to be on the device. Obviously, that would make it hard to suspend it from that point, so you'd have to put like light strings or something there. But just keep in mind, just like center of mass, the center of gravity is a hypothetical point and therefore doesn't actually have to have any mass there. All right, looking here, we can say that there is, if we look at the midpoint of the vertical part of this thing, all right, over here, there's more mass above that midpoint, which is this, than there is below, right? Because below we only have this bit, above we have that bit, but we also have all this extra mass. So that will basically drag our center of mass upward above this midpoint. So we're really at either A or D. And then if we do the same game and we look over at the midpoint of the bar, which is something like here, whoops, we still see over here that there's more mass on this side because of this bar than there is on this. So really we have to be something like A. Here we have those midpoints drawn a little bit more clearly, and so we can see more clearly that B or D can't have been the right answer, and C is sort of right off. Do notice that there's more or less some symmetry here, so we also might expect that the center of mass is along this line, and it turns out that it is. All right, these balls are connected by very lightweight rods pivoted at the point indicated by the dot and the letter P. The rod lengths are all equal except for A, which is twice as long. Circle in blue the letters with the greatest magnitude of net gravitational torque, and circle in red the letters with the least. Well, here we can see for option A, we have 1m this way and 2m here, and they're equal distance. So this is going to have a torque of 1 mg times, let's call that length L. If we look at B, we have a torque which is 2 mg at a length L. So B is definitely beating A so far. Over here, we have only 1 mg times the length L. And over here, we have mg L plus mg2L. Actually, I guess that's L over 2 and L. I guess they're saying that this length is the same as that length. So this one becomes 3/2 mgL. And so we can see that the largest case happens in this case, and the smallest cases happen here and here. All right. In both cases, a massless rod is supported by a fulcrum. That's a place where you suspend levers. It's a point of rotation, a pivot. And a 2 kilogram hanging mass is suspended from the left end of the rod by a cable. A downward force F keeps the rod at rest. Each rod is marked at 10 centimeter intervals. Fine. In which case is the magnitude of F larger? In the case where it's level, or a case where there's a bend. And to make life a little easy in talking about this, we're going to compare F to what I'm going to now just call FG. So the 200 kilograms times G. Just so we're talking about masses in both cases, because here they have mass and weight, and it's just annoying. All right. So when we look at the case on the left, case A, it's pretty clear that if we call this distance L, then we have that this distance is 3L. So we have something like FG times L on the left and F times 3L on the right. So we see pretty clearly that the force here has to be 1/3 the force of gravity, right? Fg, that we have to only push 1/3 as hard, which makes sense. We're further out, so that makes sense. And then we look at case B, and we say, well, now the lengths are going to be a little irksome because the line of action is this thing, and the line of action for that one is this, and the length that we need is from the pivot to that. This is our new, we'll call it distance S, and then we have this distance, which of course would be 3s, where we can see that S over L is the cosine of whatever angle we've gone through here. But the new distance is, of course, going to be 3s over the same angle, so we'll get 3 times as much. The new distance is going to be 3 times as much as well. But then we can say, well, then Fg times S is F times 3s, or it's still 1/3 as much. So it's the same in both cases, which is maybe a little surprising, but remember, in both cases, it's balanced, right? So they have to be, the forces have to be proportional to each other. Right. A mobile made from 3 piggy banks, A, B, and C, is shown. The banks are identical, except they contain different numbers of coins and thus have differing masses. Which bank has the most coins? Let's focus for a moment on B and C. We can see by eye that the length of the arm for B is more than the length of the arm for C. So we know that the weight of B must be less than the weight of C, because it has a greater distance, and we have the weight of B times the length of B has to equal the weight of C times the length of C. And we know that this is more, so this has to be less. Right? But then we can say that they together are now exerting a force here, some net weight FB plus FC, and we can see that that length is more than this length. So the combined weight here, F of BC, has to be less than the weight of A. So A must have the most in it. We can also see there that then B must have the least, but they didn't ask for that.